Welcome back to our networking series part 4. In this video, we will be exploring routers, switches, and VLANs, key components that form the building block of modern network infrastructure. We will break down how these essential elements work together using real world examples and use cases. We will start with the hub, its basic functionality, and how they broadcast data to all connected devices without differentiating between recipients. A comparison between broadcast, unicast, and multicast communication. We will see how switches intelligently forward data to the correct recipient using MAC addresses, reducing unnecessary traffic compared to hubs. Next, we will see at layer 3 switches how they work in exploration of how routers direct data between different networks using IP addresses to make decision on best path for data to travel. A step-by-step example showing how data flows between a switch and a router, highlighting communication and routing. An overview of VLANs, their purpose in improving network security and efficiency by segmenting a network and how they are configured. A collection of essential networking commands commonly used to configure VLANs and routings in a layer 2 switch, router setup, and layer 3 switch. We will learn about what is layer 3 switch and essential commands for configuring layer 3 switches and managing VLANs effectively in the network. Hub operates at layer 1, physical layer of the OSI model. It does not make any decision about where to send the data. It broadcasts all incoming data to every device connected to the hub, regardless of the intended recipient. If a device A sends a packet of data through a hub sends data to all devices, creating a single collision domain where data collisions happen if devices transmit simultaneously. Hub lacks traffic filtering and don't use MAC or IP addresses and sending data to every connected devices. Now let's see the comparison of different communication methods between devices. Unicast is communication where data is sent from one sender to one specific recipient. Multicast is communication where data is sent from one sender to a specific group of recipients. Broadcast communication where data is sent from one sender sent to all devices within the network or broadcast domain. Switch operates at the layer 2 of the OSI model. Switch are primarily used to connect devices within the same network such as computers, printers, servers, etc. The forward frames based on MAC addresses of devices. The switch maintains a MAC addresses table to map which devices MAC address is connected to which port. In a local network, a switch connects multiple devices to form a local area network, allowing them to communicate directly with each other. It does not route traffic between different networks. Let's suppose device A needs to send a frame to the destination device C but doesn't know the MAC address of device C. Device A sends an ERP request broadcast frame asking who has IP address 192.168.10.12. The switch receives the broadcast and forwards it to all ports. Device C, which has the IP address 192.168.10.12, send the ARP response with its MAC address. Device A updates its ARP table as cache. This ARP output on Windows OS shows IP to MAC address resolution. Next time device A communicates with the same device, it will skip the broadcast ARP request and retrieve the MAC address from the ARP cache on device. The switch learns the MAC address of device A and device C as part of this process and store them in the MAC table. In future communication, the switch will not broadcast frames between device A and C because it knows which port each MAC address belongs to, and also device has ARP records. Switches create separate collision domains per port, allowing simultaneously data transmissions and reducing collisions compared to hubs. However, they can't manage broadcast traffic efficiently. Routers solve this by breaking up broadcast domain, improving performance. Routers operate at layer 3 and use IP addresses to forward data between different networks or VLANs. We will see the VLANs shortly. This allows for inter-network communication. We will now explore how routers, switches, MAC addresses, IP addresses, and ARP protocol work together to move data from one device to another across different networks. Here's our example network. Network A has the IP range 192.168.10.0, and the network B has the IP range 192.168.20.0. A router connects these two networks, and we have switches handling communication within each network. Let's start with device A on network A. Device A wants to send data to device E, which is on network B. Let me zoom in for these two devices. The packet is prepared with device A's IP and MAC address, and the destination IP is set to device E's IP 192.168.20.11. However, the destination MAC address is left blank as it's not known yet. Since device A knows that device B is on a different network, it must send a packet to its default gateway, which is the router. To do this, device A needs the router's MAC address, so it sends an ARP request asking who has IP address 192.168.10.1. The router replies as ARP response with its MAC address, which is updated by the switch and added to device A's ARP cache table and added to the frame. Device A sends packet to the router which using the router's MAC address. The switch forwards the packet based on its MAC address table, ensuring it reaches the correct destination. The router receives the packet on its network A interface and start inspection. It will check the layer 3 information, which is the destination IP address. It determines that the destination IP is on a different network, network B. The router consults its routing table and prepare to forward packet to network B. Before forwarding the packet to device E, the router need to know device E's MAC address. The router sends an ARP request on network B to resolve the MAC address for 192.168.20.11 device B's IP destination IP. Device E receives the ARP request in response with its MAC address. The router now updates its ARP cache with the information IP address 192.168.20.11 and MAC address of the device E. The router sends the packet to switch B, which then forward it to the correct port where device E is connected based on the switch MAC at table. Device B receives the packet, check the destination IP and MAC, and process the payload. The packet's payload carries the actual data, and port number ensures the data is directed to the correct application on the destination system. Now that we understand switches, routers, and traffic flow between them, it's clear that adding new network often requires adding physical switches. As organizations grow, this can lead to complex, inefficient network design and increased security risk, significantly complicating management. VLANs allows us to logically separate devices into different networks even though they are connected to the same physical switch. Each VLAN operates as its own isolated network. Each VLAN creates its own broadcast domain. This reduces the overall broadcast traffic. VLANs enhance security by isolating traffic, preventing unauthorized access, and separating departments like sales and HR unless allowed. While VLANs segment traffic within a switch, devices in different VLANs need a router to communicate with each other. The router enables inter-VLAN communication by using IP addresses to route traffic between VLANs and external networks, ensuring connectivity. A router on a stick setup connects multiple VLANs to a router using single interface with sub-interfaces, enabling the router to route traffic between VLANs such as VLAN 10 and 20 through a trunk link on the switch. Access ports connect end devices like computers and printers to the network. Each access port is configured for a specific VLAN, ensuring that the connected devices is part of that VLAN. Trunk ports are used to carry traffic for multiple VLANs. They allow VLAN tagged frames to pass between switches or between a switch and a router, ensuring that the traffic is directed to the correct VLAN at the other end. Routing rules enable inter-VLAN communication by allowing traffic between isolated VLANs through defined sub-interfaces or configuration. To prevent communication between VLANs, routing rules must be configured on the router's sub-interfaces. These rules specify which VLANs are allowed to communicate with each other and ensure that traffic flows correctly between them. For example, if I need to send a packet from device A in VLAN 10 to another network device E, the packet will first be sent to the switch. Since device E is in a different VLAN, the switch forwards the packet to the router. The router checks the packet source and destination IP. The router verifies whether the routing rule allows traffic between VLAN 10 and VLAN 20. If the rule permits traffic and a route is available, the router forwards the packet to device E in VLAN 20 via the same switch. VLAN 10 and 20 are created and given the name as HR department and IT department respectively. In this example, access port are assigned to the VLAN 10 on the switch port using these commands on the switch. Access port assigned to VLAN 20 on the switch port. A trunk port is configured between the switch and the router to carry traffic for VLAN 10 and 20. Sub-interfaces are configured for each VLAN on the router. Each sub-interface is assigned an IP address within the respective VLAN subnet. This IP address like 192.168.10.1 and 192.168.20.1 will be the default gateway on router for the VLANs. The encapsulation.1q command is used to associate each sub interface with the appropriate VLAN. IP routing is enabled to allow communication between the VLANs. Once the configuration is complete, devices in VLAN 10 should be able to communicate with devices in VLAN 20. A layer 3 switch combines the functionality of both a switch and a router. It operates at the network layer, routing traffic between different VLANs or subnets using IP addresses while also functioning as a layer 2 switch within the same network. In this example, a modern switch handles both intra-VLAN traffic as a layer 2 device and inter-VLAN traffic as a layer 3 router. This dual functionality optimizes network performance. VLAN 10 and 20 are created similar way we done previously. Access ports are assigned to the VLAN 10 on the switch port. Access ports are assigned to VLAN 2 on VLAN 20 on the switch port. We need to create switch virtual interfaces for each VLAN and assign IP addresses to them. These IP addresses will serve as the default gateway for the devices in their respective VLAN. This configures the VLAN 10 interface. with the IP address 192.168.10.1, which will act as the default gateway for the devices in VLAN 10. This configures the VLAN 20 interface with the IP address 192.168.20.1, which will act as the default gateway for the devices in VLAN 20. By default, layer 3 switches don't perform routing until IP routing is explicitly enabled. We need to turn on IP routing to allow switch to route traffic between VLANs. That's it. We have completed the section on router switches, VLANs, and layer 3 switches, along with examples and how they work. In the next video, we will cover troubleshooting. If you found this video helpful, don't forget to like, subscribe, share, and leave a comment with any question. Thanks for watching and happy networking.